Okay, so radicals we know as roots. We solved it last year. We did lots of work with radical equations. We rationalized denominators. We rationalized denominators with two terms. Now what we're going to do is we're going to take radicals and we are going to graph them. So with that being said, we usually stick in the square root world. Okay, we don't normally go past the square root world, and you'll be grateful for that. So we're going to look at positive principal roots. Do you guys know what that means? We talked a little bit about it last year. Positive principal roots. When you take the square root of 4, what do you get on your calculator? Positive 2. So the positive is your principal, so your first root. So we're going to be looking at just using our positive answers. How does that make you feel? I think it's good and bad. Like, it's nice because it's less complicated, but it's bad because we use both roots in like solving our trig equations and things like that. So it gets a little bit confusing, but we're going to graph our basic radical graph. We always have a basic graph, and that's the table of values that we're going to do our transformations to. So this one's nice and easy. We're going to do our table of values. So I'm going to be purposeful with the x's I pick. I'm going to be purposeful with the x's I pick. What kind of x's do you think I'm going to pick? If I have to square root them, what kind am I going to pick? I'm going to pick perfect squares that root nicely. Like, I'm not going to pick x as 2. Because then we're going to get the root of 2, which is a decimal, which isn't very nice. So the x's that I'm going to pick are very purposeful, and I'm going to pick perfect squares. What's the very first perfect square?
4. 1.
0. What's the next perfect square?
1.
Okay, so I'm being purposeful with them just because I want my table of values to be kind of nice. All right, what are my y values now? What's the square root of 0? Square root of 1? Square root of 4? 2? Square root of 9? 3. Okay, so I'm going to deal with the positive principal roots. I don't think it's principal, it's principal. Sorry. L-E, not A-L. Okay, now we're going to graph it. Easy peasy, right? Now, could this graph go on forever? Yep. Why do I not have an arrow on the left-hand side? Nope. Nope, that's the y values.
Oh, because it starts at disclosed point.
Nope. Okay, let's try this. What's the square root of negative 2?
Impossible.
It's impossible. So that's why we have no negative x values, and that's why it starts at 0. Okay? Because we can't take the square root of a negative number. We'd get not an impossible, we get an imaginary number. So nothing we could graph. So we can't use negative x values. But that's not a true statement. We're not applying an absolute here. This is an impossible. It doesn't work, right? So we didn't apply any absolutes. We didn't do anything with that. Ooh, speaking of absolutes, while we're on the topic, provincial exam is really a big fan of giving you an absolute graph and asking you to apply transformations on it. We did absolute graphs in grade 11, and we don't do them in grade 12. We did do, however, transformations, and any graph is fair game with those transformations. And I've seen the absolute graphs show up more than once. So you may want to take a look through past provincial exams and look at the questions they're asking you about absolute graphs. And we can review it for sure, like we can go over it and review it, but just know we won't be doing any graphing on absolute graphs. Like we won't be revisiting that unit. Okay, so that's your basic one. So let's go through this again. All right, so if you graph and you have an equation, so it's not function notation, there's no F in here, this is equation format. A results in a vertical stretch. The A itself is absolute. It's kind of like our amplitude in sinusoidal graphs. It does the stretch. If it's negative, what does it do? It's a reflection, right? So the negative does something else. So if A is less than 0, the graph, so if A is, let's write that, if A is negative, the graph will reflect in the x-axis. Okay, B, horizontal stretch by a factor of 1 over B. If B is negative, it'll be reflected in the y-axis. H is a horizontal shift, and K is a vertical shift. We good? Okay. All right. Let's do some transformations. We're going to transform them, and we're going to do the domain and range. I'm just putting my basic table there because I think now we're not going to graph with patterns like we did in sinusoidal functions. We're going to graph using our transformations. All right. Maybe I'll switch colors here. So what is this telling me to do? Where are we going with that one? 2 to the right. Mathematically, what is it telling me to do? What mathematically is it telling me to do? It's like we're going back to chapter 1, folks. What's the mapping rule on this? What am I doing to my x's? Remember that x isn't going to do the same. It's not going to give you, you're going to do the opposite of it. And then the plus 1. We're going to shift 1 unit up. So our y's are going to be plus 1. So when we create the new table of values, and I find doing a mapping rule is helpful because it tells me exactly the math that I need to do. X's are going to be added to 2's. 2, 3, 6, 11. And y's, we're going to add 1. All right, so 0.00. This is our start point. Remember that this was a closed circle. That was our closed circle end point. So now that point translates to here. So that becomes our start closed end point. So with the radical graphs, we have to make sure that we pay attention to where this point translates to, because we need to mimic that same end point. So now I'm at 2, 1. So let's go ahead and graph that. All right, I'm going to go ahead and graph that. So over 2, up 1. And my 11.4 is off the graph. So that's my beginning point, and that's going to have the arrow there. I need a calculator for a second. Okay, I forgot a very important part. Can we go back to the first graph for a second? Do you guys have a handy dandy calculator in front of you? No? Okay, I'll put mine under there. So I want to add a point in. I want to add a point in there for a second. So I did it on my calculator. Oh, that's very dark. So if I take the square root of 0.5, what do you notice about the answer? It's actually bigger. When we take the square root of the decimal, it's actually bigger. And then now I'm going to do the square root of 1.1, just for funsies. And that one's smaller. So what I need you to know is between the point 0 and 1, the values are actually greater than their x value, which seems counterintuitive, right? If we take the square root of 4, we get a smaller number. But with decimals, things happen a little bit more oddly. So if we're at 0.5 here, if we're at 0.5, this is 0.7. What you need to know is that from 0 to 1, this kind of bubbles up, and then it continues on. So we should have a little bit more of a bubble there. Do you need to graph those points exactly? No. But it's a weird bubble on the top of it. It doesn't need to be exaggerated, but it does need to be there. And that bubble has to follow you in all of your transformations. Okay? Mathematically speaking, it's there, and it only happens between 0 and 1. After that, it follows kind of the pattern of what we think numbers should do. So when I go to do my second graph, I should see a bubble here. Actually, that's not this is not bad if you're redrawing your graphs, because then you can see the difference in the bubble between my original line. That is technically the correct shape of a radical graph. Okay? with that little bubble between the first and second point, even with the translations. Okay, next one. There's something we have to do before we graph.
There's a negative sign for x.
Yeah, what do we got to do with it? We got to common factor that out. Now we can do our transformations on it. So, we have a vertical stretch by how much?
Two.
3. Remember, anything vertical, it's straight from the equation. What does that -1 tell me I have to do? Reflection in the y. And the subtract one? So this is just chapter 1 all again. This would be me describing the transformations. If I were to create a mapping rule like I like to do, because I find it helps my head get organized, we know that the x's are going to be multiplied by -1, and then we're going to add 1 to it. And the y's we're going to times by 3. So even though it's a reflection in the y-axis, it's math we're doing to the x values. I'm going to put my original chart there. Did you guys get those X's? Or are you copying mine? Today might not be the day to copy mine. And I find it hard to see the picture just from the coordinate pairs. I definitely have to graph it, but I like writing this out too, or at least knowing it in my head, because I need to know that it's reflected in the y-axis. So if it's reflected in the y-axis, which way, before I graph, which way do we anticipate the graph going? Is it going to point to the right or is it going to point to the left? Should point to the left, right? So should be pointing to the left. I know that my graph's going to be 1 unit up, so I'm not going to be at 0, 0. So I can kind of envision it from the description better than I can from the numbers. And maybe you're a different thinker, and that's okay, that's awesome. And you can see it, but I struggle with seeing it. That should be a 10. All right, so if that point translates to, if that point translates to that point, we know that that is our closed circle. That's where our graph is starting from, that no arrows on that. So 1 and 0. All right, then we have 0 and 3. -3 and 6. -8 and 9. What do we know between these 2 points? What should we have? We should have that little bubble, right? So it's not going to just be connecting these 2 points. We're just going to bubble up a little bit. So nothing too terrible. It's just your chapter 1 attached to radicals. Just your chapter 1 attached to radicals.
Chapter 1 always has the general.
And I did tell you that.
Is the little bubble always right around the first 2 points?
Yep, always the first 2. Okay. Again, I got to do a little bit of math before I can do my transformations here. I'm going to add 3 to both sides, so y equals -√2x plus 3. The 3 is outside of the radical sign. The negative outside tells me what? Yep, reflect in x-axis. We have a horizontal stretch by a factor of how many? 1/2. Ladies and gentlemen, I got to tell you, if you were asked to describe, you need to use these words. Horizontal stretch by a factor of. Okay, you need to use those words because that means you're multiplying. And then we have a vertical shift. Three units up. Oh guys, I was supposed to do the domain and range for these graphs. Yeah, I was. Not a hard thing. Do you guys remember when domain and range was hard in grade 10? It was hard. No, it was never hard. Okay, we'll graph this one, and then we'll go back and do our domain and range on these. This question didn't ask you to do this, but it's good that you get into the habit of at least thinking about it. And it really doesn't take that long to write it down. Oh, I didn't do my mapping rule. And again, you don't have to do a mapping rule. It's just super helpful if you're like me and can't really see it. So my x's are being times by 1/2, and then everything else is happening to the y's. I am all over the place. I used fractions, I used decimals. Are you guys confident in doing that? So again, starting point to new starting point. That's that closed circle. All right, let's graph our table of values. Changing my scale on this one. So these would be my first 2 points. So I'm going to bubble through them. Okay, now we need to do domain and range for these graphs. Are you guys graphed?
Can you set notation?
No, we're gonna do interval notation. If you choose to do set notation, perfect. But I think the majority of us in here are comfortable, but if you want me to check your set notation, I'd be more than happy to do that. All right, let's look at this graph. So the domain on this graph, where are we going? Inclusive is 0 to positive infinity. And the range? Right. So even though we see the 3 first, we know that it's going down. So we have to start with the lower limit. So negative infinity to 3, and that's inclusive. Slide up here. This graph for the domain, we're going to have negative infinity to 1. And the range, we're going to have 0 to positive infinity. I don't think doing domain and range is hard anymore. I think remembering to do it if the question asks you to is the hard part. And then this little graph here, domain, we start at 2 and we head to positive infinity. Range, we start at 1 and go to positive infinity. Again, your square brackets have to be significantly square. Like I shouldn't be questioning whether this is a square or round bracket. So just keep that in mind when you're doing your domain and range. Okay, pretty easy, right? All good. All good. Okay. Okay, here we go. Let's draw on our original graph because that's what's missing here, is let's draw on the y equals root x graph. That might be helpful. Pardon? Sorry? I'm putting this graph on there, like the original table of values. Right away, what can you tell me about this graph? What can you tell me we don't have on this graph? Let's see how much you remember from chapter 1 or if you blocked it out. No horizontal shift. No vertical shift. How do I know that? No reflection. Okay, we got 3. How do we know about the horizontal and vertical shift? There is definitely a stretch. Now we just got to figure out horizontal or vertical, and we're actually going to do both. We're going to do like option 1, option 2. The reason why we know there's no shifts on this, how do we know that? Our starting point, that's 0, 0. When I'm looking for a shift, when I'm looking for the graph to shift, and I think some people mess this up on their chapter 1 test, which is okay because you can redo it and get better. When you're looking for the shift for horizontal, you're looking for a point that x is equal to 0. because that's the only point that a stretch will not affect it. Luckily, this graph starts at 0, 0, so we see that it's shared. If there was a shift, when x is equal to 0, we'd see that at another place. Because even if there was a stretch, 2 times x, if x is 0, is still 0. The only thing that would affect it would be an add or subtract. So when we're looking for shifts, you're looking for horizontal, x equals 0. If you're looking for vertical, you're looking where y equals 0. Has there been a change? And there hasn't. We know that there's no reflections here because it's not kind of cupping up and it's not going to the opposite side of the y-axis. Okay, so we got those out of the way. Right now we know, so if the form is y equals a root b x minus h plus k, what did we decide? No h, no k, and we know that a and b are positive. So we did all that math by just looking at that graph. Okay, so 2 equations that are going to result in the exact same graph. We're going to do one with a vertical stretch, and we're going to do one with a horizontal stretch. Okay, so option 1. Are you guys okay with the light blue pen? Can you guys see it okay? I never asked somebody. Okay, so option A, let's go with a vertical stretch. Let's go with a vertical stretch. So we're going to assume that there's no horizontal stretch. So we're going to have y equals a root x. Because what do we know h and k are? There's 0, right? We said there was none. So I dropped those right away. Is everybody okay with that? And we know that A deals with the vertical stretch. So how am I going to deal with this, ladies and gentlemen?
You fill in your x and y values and then you solve for the a.
Brilliant. So you're going to pick a point, any point on the transformed graph. What point are you guys going to pick?
1, 1.
That is not the transformed graph. How about we pick 4, 1? Okay, so we're going to pick any point. We're going to pick a point, 4, 1. That would be our x, that would be our y, and we're going to substitute that value in. So we are going to have 1 equals a root 4. 1 equals 2a So we would have an equation, y equals 1/2 root x. Okay, good job, everybody.
Can you put like
The half has to go inside the root side.
Pardon?
The half has to go inside the root.
Outside, yes.
Inside.
Nope.
Can you do a root x
Yeah, that's
divided by
inside.
2?
It's not the same one.
Nope, it is.
Just put it where it is.
Okay, now what we're going to do is we're going to do option B. Where we're going to look at a horizontal stretch. So this time, we have y equals bx. All right.
Why is there a b inside the root cell?
Holy Hannah, pardon?
Why is the b inside the root cell?
B's are related to the x, and they have to be under the root sign if they're going to affect the x. All right, so again, we know we don't have an h and k because we talked about having no shifts, vertical or horizontal. We have no reflection, so we know B has to be positive. We're going to pick a point on the graph. I'm going to stick with what we know. And it's the transformed graph, right? Like, because that's we're trying to find the equation of the transformed graph. I just graphed the blue one on there to be our helper graph to see that there actually was a transformation done. So we would have 1 equals root 4x. How do I, oh, sorry, that should be 4b. 4b, not 4x. How do I isolate the letter b? Square both sides. So my equation would be y equals oops.
Can I just simplify the radical? So you can do like y equals to half multiplied by root x.
Wouldn't that be exactly that?
Yeah. Oh.
So this is telling us that we're taking our y values and timesing them by a half, and this is telling us that we're taking our x values and timesing them by 4, correct? That's what that tells me. All right, just give me 1 second. I'm just doing, some graphs for you here. Ooh, that's not what I wanted. Hannah, 2 is good, and x is fine. Okay, so I'm going to turn that off again just so we can see it. Okay, so we have those two equations in, the 1/2 outside and the 1/4 under. So if I go ahead and hit graph, so there's my first graph, that's the 1/2 graph. And the red graph that's following it is the 1/4. They result in both graphs. And if you're not sure or you don't trust that this is the same graph that's on there, let me grab, so we said when x is 1, what is it on the graph on your page? What's the y value? Guys, you just need to look at that graph. What's the y value? Hopefully it's 0.5. Everybody see that? The y value is 0.5 when x is 1. And when I put in an x value 1, the graph is 0.5. So what I'm just trying to show you is that just like sinusoidal functions, you can do two different equations and get the exact same resulting graph. Okay? So just because you've done your stuff differently doesn't necessarily mean that it's incorrect. You know what I mean? So we can accomplish these both ways. All right. Okay. Here we go. Determine the equation of the function shown and the equation of its reflection in each quadrant. The transformations are done to the graph y equals root x. All right. So, quadrant 1. Are there any reflections? is this our y equals, well, maybe let's figure out, is this is our y equals root x graph? No. Where's our y equals root x? 0, 0, 1, 1, 4, 2. So that is our y equals root x graph. Okay, so in quadrant 1, this is in quadrant 1. We need to figure out an equation for this one. Any shifts? Left or right? Up, down? This is a nice one. This is nice because it always has that starting point of 0, 0. If the starting point is still 0, 0, you have no shifts. You have no shifts. So we're looking at stretches now. What's the easiest stretch to see? This one was 1, now it's 2. This one was 2, now it's 4. So what's happening to the y values? Y values are times by 2. That's the easiest one to see. You could do it as a horizontal as well. But the easiest one to see is that it's vertical. So in quadrant 1, y is equal to 2 root x. Would everybody agree with me? Nice and easy, vertical stretch of 2. I'm walking away. What's the equation if this graph were reflected into quadrant 2? So now this graph is here. This graph has flipped over here. Anything change with my stretch? My x is negative now. So y equals, because that's a reflection in the y-axis, so it's going to be math happening to the x. Going to leave quad 3 for a second. We're going to go to quad 4. So now this one's doing that. This one's reflecting here. So what's this one going to be? So we're going to have y equals negative 2 root x. Nice and easy. It's a reflection in the x-axis this time. So the math is applied to the y. So that's why this is negative. Okay, quad 3. Anybody want to hedge a bet? So you'd have a reflection here into the second quadrant, and then you'd be reflecting into the third quadrant. So you would actually have 2 reflections here. This would be y equals negative 2 and negative x. Not a lot of math to calculate there, but a lot of mathematical understanding just went into that question. All right. This looks ugly, but is easy. People see this and they're just like, no, I'm out. I don't want to do anything with it. I don't want it. No, looks horrible. So when we're talking about the domain and range, I think the easiest thing to do would be to do the basic graph and then do the transformations on it. So if I were looking at this basic graph, that would be s equals root t. Right? Everybody agree with that? All right. We got to do some unmathing. To see the transformations. I'm going to go here for a sec. This one's pretty easy. What do you see right here? We got a vertical stretch by a factor of 331.3, right? That's nice and easy. We can do that. It's what's happening under here that's a little bit ugly. So I'm just going to do some math on this side. Nobody's shocked by that math. I just switched the places of the two. How can I, okay, better question. If I give you this, how would you deal with that to see the reflections or the transformation? Sorry, there's no reflection there. What would you guys do? I'd have to common factor out that coefficient of 2, right? And we'd be left with 2 on the outside, x plus 1/2, right? You guys all know that strategy. You did it really well on the sinusoidal graphs. We practiced it in 1. So we're going to do the same thing here. This is just like saying it has a coefficient. It's like saying you have a coefficient of 1 over 273.15 times t plus 1. So we need to common factor that out of everything because we need it to look like this. We need it to have that bracket around it so that we understand what the transformations are. All right, so if we take this out of both terms, that 331 is still sitting there. And if we take it out of both these terms, what happens to this 1? Plus 273.15. So I divided 1 by 1 over 273.15. Because what do I have to multiply this by to get it back to 1? I have to multiply it by that numerator. So now, once you do some math, like this is the easy stuff. This is the stuff that we had. You're going to apply those same principles right here. You're just common factoring out that coefficient. Just so happens that the coefficient is an ugly fraction. And we got to be okay with dealing with ugly numbers. All right, so my start point on the basic graph is where? 0, 0, right? Basic graph starts at 0, 0. With these transformations, will the y be affected?
Yes.
No. Right, because we times 333.1 times 0, what does it give us? 0. All right. Will it be affected by the horizontal stretch? Because that's a multiply thing. Is it going to be affected by the horizontal shift? Yes. This is the point where, which direction am I going? I'm going left because it's an add. So for the domain, I'm going to start my graph at negative 273.15. Were there any reflections here? Were there any reflections? No, so I know I'm traveling in a positive direction, so that's going to go to positive infinity. Range is going to be the same as the basic graph. How do you guys think you would have done on this one? Would you have known to common factor? Probably not, because you probably weren't thinking that way. Would you have graphed it using a table of values? Maybe, just to get some starting points. It would be ugly and it would be hard to do, but you would get them. But transformations is going to automatically take you to your first start point. Okay, easy peasy, guys. Now we're just doing math. Now we're just pumping this in. So determine the speed of sound to the nearest meter per second at each of the following temperatures. We're just dumping this into the equation. This is a plug and chug at this point. And you can go back to the original equation if you prefer. Oh, that's supposed to be a 1. Okay, I need you to try this in your calculator. I need you to try that in your calculator just so you know if you're using your calculator correctly. Solve that. You can't see it? Is that better? These are just plug and chugs. You're putting the number in, you're putting it into your calculator. You're just going to see if you know how your calculator works. No, we're not using angles. We're not using sine or cos anymore. So you're golden. You can be in whatever you want because we're not accessing that. All right, so I threw in all the decimals, and what I wanted to show you was the order in which I did things in. And the only reason why I wanted to show you that is I can put it all into my calculator as one thing, and my calculator will do it for me. But if I couldn't do that, I did the division first, got the decimal, added 1, got that answer, then square rooted that, and then times by 331.3. Like those were the steps that I went through in my calculator, because remember that under the root sign is treated like a bracket. I don't think we need to go through the rest of them. They're all just going to give us different answers. I can give you the answers if you just want to check them. If it's 0, it's going to be 331.3, we're 3331 meters per second. If it's 63 degrees, that's going to be 291 meters per second. And the last one is going to be 272 meters per second. That's a sketchy 2. Those are just plug and chugs in your calculator. I just wanted to take the opportunity just to make sure we knew how to use our calculators.
Is it negative 63 or positive 63?
Oh, sorry, it should be a negative. You're right, Rahat. I apologize. That should be a negative there when you put, it should be negative 63. I don't know where that went. All right, that is your first lesson.